The Boys anti-tank rifle entered service rapidly. Design authority resided under Captain Henry Boys. Development began during pre-war British rearmament programs. Primary threat assessment focused on light armored vehicles. German armor estimates underestimated future protection growth. British infantry lacked organic anti-armor capabilities. Existing artillery assets lacked tactical mobility. Rifle solution pursued due to industrial familiarity. Small arms factories could adapt tooling quickly. A shoulder-fired weapon reduced logistical burden assumptions. Caliber selection favored extreme projectile mass. The .55-inch cartridge exceeded previous infantry precedents. Projectile diameter measured approximately 13.9 millimeters. Cartridge case length reached 99 millimeters. Propellant charge mass exceeded typical rifle tolerances. Chamber pressures surpassed conventional shoulder weapon norms. Action design selected a bolt-operated mechanism. Bolt lugs reinforced to handle elevated pressures. Receiver machined from solid steel billets. Weight increase accepted to ensure structural integrity. Overall unloaded mass exceeded 16 kilograms. Length measured over 63 inches. Barrel thickness increased significantly toward chamber. Rifling twist optimized for heavy steel cord projectiles. Muzzle brake incorporated to mitigate recoil impulse. Brake employed multiple baffle ports forward-facing. Gas redirection attempted to counter rearward momentum. Brake efficiency limited by extreme projectile energy. Recoil spring added within butt assembly. Spring absorbed rearward bolt carrier motion. A butt plate incorporated sliding recoil mechanism. Shoulder interface used hardened steel surfaces. Padding considered insufficient under operational conditions. Trigger pull weight increased to prevent accidental discharge. Sear engagement surfaces hardened for durability. Magazine design utilized detachable box configuration. Magazine capacity limited to 5 rounds. Feed lips reinforced to prevent deformation. Cartridge rim diameter complicated stacking geometry. Feeding reliability varied with manufacturing tolerances. Bolt travel lengthened to accommodate cartridge length. Cocking effort exceeded average infantry expectations. Manual operation slowed follow-up shots significantly. Rate of fire depended heavily on operator strength. Training manuals emphasized prone firing positions. Standing fire discouraged due to recoil forces. Crew operation recommended despite single-user designation. Assistant gunner role unofficially adopted in practice. Ammunition weight limited carried load significantly. Each cartridge weighed approximately 200 grams. Infantry loadouts reduced to minimal quantities. Resupply requirements strained early war logistics chains. Penetration tests conducted against mild steel plates. Early trials demonstrated success against thin armor. Armor thickness tested ranged below 30 millimeters. Penetration achieved at short engagement distances. Velocity dropped rapidly beyond 100 meters. Accuracy suffered due to recoil anticipation effects. Operators reported bruising after limited firing sessions. Medical reports documented clavicle stress injuries. Some units recorded fractured collarbones. A muzzle blast generated extreme overpressure effects. Nearby personnel experienced temporary hearing loss. Dust signatures revealed firing positions immediately. Concealment compromised during urban engagements. Cold weather affected recoil spring performance. Lubrication thickening increased bolt resistance. Arctic trials identified cycling difficulties. Sand ingress disrupted bolt operation reliability. North African trials exposed maintenance challenges. Barrel heating limited sustained fire capability. Thermal expansion altered point of impact. Cleaning regimen required specialized tools. Bore fouling increased with steel core ammunition. Replacement barrels not field swappable easily. Manufacturing required precision machining capacity. Tooling time exceeded optimistic production estimates. Skilled labor shortages slowed output rates. Contract disputes emerged between subcontractors. Inspection rejection rates increased during peak demand. Quality control struggled with pressure tolerances. Rejected receivers required extensive rework. Cost per unit exceeded alternative concepts. Procurement officers raised concerns regarding sustainability. Field reports questioned tactical relevance rapidly. German armor upgrades reduced effectiveness quickly. Increased sloping diminished penetration probability. Tank side skirts defeated projectile performance. Infantry confidence in weapon declined sharply. Operational doctrine shifted toward shaped charge weapons. Research redirected toward spigot mortar concepts. PIAT development overlapped with Boys deployment. Boys rifles reassigned to secondary theaters. Use continued in Pacific and Arctic environments. Japanese armor vulnerability extended limited relevance. Improvised anti-material roles adopted unofficially. Targets included pillboxes and light vehicles. Barrel wear accelerated under non-standard usage. Spare parts shortages complicated long-term service. Official doctrine ceased emphasis on rifle solution. Production contracts curtailed before projected quantities. Surplus rifles placed into storage rapidly. Post-war evaluations criticized ergonomic shortcomings. Medical assessments influenced future design prohibitions. Man-portable kinetic anti-tank rifles deemed obsolete. British doctrine shifted permanently toward explosive warheads. Lessons incorporated into later infantry weapons policy. Engineering emphasis moved away from brute force. Recoil mitigation considered primary design constraint. Boys' rifle categorized as transitional failure. Documentation archived with limited public dissemination. Weapon quietly withdrawn without ceremonial replacement. No direct successor pursued by British industry. Historical assessment framed weapon as desperation artifact. Post-war storage conditions caused corrosion issues. Protective finishes proved inadequate for long-term warehousing. Cosmoline application varied between depots. Bolt assemblies seized under prolonged neglect. Wooden stocks absorbed moisture unevenly. Cracking developed along recoil channel in butts. Metallurgical reviews noted stress fractures near locking lugs. Heat treatment inconsistencies amplified failure risks. Proof testing margins left minimal safety buffers. Ammunition production ceased before rifle retirement. Remaining stockpiles deteriorated chemically over time. Cordite stability decreased under tropical storage. Case neck splitting observed during later inspections. Projectile core bonding separated under aging conditions. Disposal policies avoided refurbishment investment. Foreign military aid programs redistributed surplus units. Recipient nations reported similar recoil complaints. Training accidents prompted further restrictions. Some rifles modified for ceremonial drill use. Live firing officially prohibited in several commands. Armor penetration charts removed from manuals. Doctrine publications revised to exclude rifle-based solutions. Engineering committees cited human tolerance limits. Ergonomics studies influenced future weapon procurement. British Army Medical Branch formalized injury reporting. Data shared with Allied Ordnance departments. American evaluations confirmed operational impracticality. Comparative trials favored shaped charge launchers. Cost-benefit analysis disfavored kinetic penetration systems. Industrial planners reallocated machining capacity elsewhere. Barrel steel contracts repurposed for artillery. Receiver forgings reassigned to vehicle components. Training schools eliminated boys-specific instruction. Ammunition depots decommissioned specialized storage racks. Maintenance manuals withdrawn from circulation. Technical drawings archived under restricted classification. Public references minimized during post-war narratives. Museum examples often rendered inert permanently. Live examples subjected to deactivation protocols. Bolt faces welded or milled intentionally. Bus chambers plugged to prevent cartridge seating. Muzzle brakes frequently removed for safety. Curatorial notes emphasize injury statistics. Veteran testimonies corroborate documented hazards. Operational lessons informed NATO small arms philosophy. Recoil energy calculations standardized across programs. Human factors engineering gained institutional priority. Subsequent British weapons reduced impulse dramatically. Infantry anti-armor doctrine fully transformed. Kinetic rifle approach formally abandoned permanently. Boys' rifle remains studied for failure analysis. Its existence illustrates limits of brute engineering. Design reflects pre-war threat miscalculation. Manufacturing urgency outweighed ergonomic evaluation. Procurement pressure compressed testing timelines. Operational feedback arrived too late. Institutional inertia delayed withdrawal decisions. The rifle persisted beyond usefulness window. Administrative withdrawal executed quietly. No official condemnation issued publicly. Internal memoranda recorded harsh assessments. Weapon classified as emergency expedient. Lessons integrated into future procurement safeguards. Design review boards expanded authority afterward. Medical clearance incorporated earlier into trials. British infantry never fielded similar system again. The boys' rifle stands as a cautionary artifact.